Welcome to the 21st class meeting of EECE574, the graduate level probability and random processes. As usual, homework 11 will be posted on the PLMS, and the quiz number 2 will start at the end of this class meeting. So the problems will be available from 12 something, let's say 20 today, and due is not exactly in 48 hours, but just before. Actually, I had to say that it's 10:59 a.m. on this Thursday, May 2nd. Handouts for this chapter 7 is updated again, so you'd better download it. Handouts for chapter 6 are posted also. I've intentionally separated each sections so that you don't need to download all of them again and again. Messages from instructor, you have no interest because of case 2, so let me skip. Overview. So we are going to finish this chapter 7, and fortunately, the random process part will not appear on this second quiz. So today's probably half of the material will only be covered by quiz 2. There is a clarification. I will talk about it while we are reviewing last class meeting. So last time, we talked about the background materials for Borel-Cantelli lemma, and we just stated the first and second Borel-Cantelli lemmas. And what were they? And it was something similar to the our undergraduate stuff that shows something like this. Suppose you have some non-negative number sequence, and you sum up all of them and they are finite. Then what can you say? If you consider a partial sum of this piece of n's, then you know that the limit p sub n as n tends to infinity converges to 0. And it's obvious. You learned it from your high school math and you proved it several times. The Borel-Cantelli lemma looks very similar to it. The difference is that now you have a sequence of events. Let's say A sub n. And of course, the probability of these events are non-negative real numbers bounded by 1. And now you sum up all of them. And similar to the previous reference result of your undergraduate or high school math, you have a finite sum. Then, of course, by the previous one, you have the probability sequence, not the sequence of events. The probability sequence converges to 0. The Borel-Cantelli lemma is not about this one. It's more than this one. So we have here the lim sup of an equals 0. That is the Borel-Cantelli lemma. And sometimes lim sup is stated as what? Lim sup is what? By the way, this can be written as lim inf of an complement is 1. So you see the similarity. Am I correct? Let me check it again. It's always confusing. Yeah. So you have sum of probability of events that are finite, and then not just the limit of the probability sequence, but the probability of lim sup of the sequence equals 0. And as I told you, this result is very useful when you want to prove something converges almost surely. And this is called the first Borel-Cantor lemma. What about the second Borel-Cantor lemma? And the second one was what? Was kind of inundated, flooded by this in. What was that? You have now independence. Independence of these events. And again, you have sum that is infinity. So independence, infinity. And then what? By the way, you never have some, you sometimes have this one, but it may diverge, right? For example, if you have 1 over n sequence, even though you have the limit of 1 over n converges to 0, sum of 1 over n diverges, right? And here, the result is that lim_inf equals 1, if I remember correctly. Okay, so sorry, lim_sup equals 1. Again, it's always confusing. Okay. Okay. Not this. Same lim_sup, but equals 1, something like that. Got it? So these are Borel-Cantor lemmas. After I talked about that, I covered a lot of material about random number generation. Today we are also briefly talk about it, but anyway, so there is no pure random number if we use computers. So if we don't rely on some quantum physical system, there is no pure random thing. So we use computer to generate pseudo random numbers. And one of the reasons why we need these random numbers is for the Monte Carlo integration or simulation. And this Monte Carlo simulation or integration was to find some integration of, for example, something like this. So you want to compute the integral of a function. Unfortunately, sometimes this integral is very complicated, and even more, you have a black box, so you don't have exact mapping rule. You can only use this black box to apply your input and to get the evaluated version of the function at that input. In that case, how can you integrate this one? And one interesting idea is to convert this integral into the product of the function times the density function of the, in this case, continuous uniform random variable. Then you can rewrite this integral as expectation of g of u. If you say u is a uniform random variable. And then what can you do? We can rely on, as it states, the law of large numbers. So this can be well approximated by what? G of u1 plus g of u2, up to g of un. Got it? So the basic idea of Monte Carlo integration is that you use a random number. Got it? And this can be applied in many cases. For example, as we see, I will cover it soon. I don't need to diverge it. Anyway, sometimes what you want to do is something like this. we multiply and divide by some f. And suppose this is a probability density function. Then what can you do? You can rewrite this one as something like this, right? So instead of directly integrating g of x on this 0, 1 interval, sometimes you may have a random number that is not necessarily uniform on 0, 1, but in this case, a random number between 0 and 1. And then you multiply and divide. Let me divide. Multiply and divide and generate random number x so that you can well approximate this one. By the way, such a technique of divide and multiply is called importance sampling. Got it? So here, clarification. Yeah. The reason why this is called sampling will be apparent if we move to today's material. But that trick I mentioned last time is called importance sampling. So instead of directly using some density, we deform the integrand function and then use Monte Carlo integration. So that is one of the idea, and this is very important to evaluate some expectations, right? So every probability can be written as an expectation of the indicator function. So in order to evaluate some probability, in order to get some approximate value of the probability, we can always use this Monte Carlo approach. Then we need to ask, how can we generate a random variable? And then how can we generate multiple random variables that are dependent? So the first topic was, and we already know how to generate a continuous or discrete random variable from a continuous uniform random variable. And that is very easy, right? You can use the CDF. So in this case, from U to X, you just use the CDF. Just a second. Not CDF, percentile function to generate. And this gives us some idea like this. We can generate any function, any distribution from any other distribution as far as this is continuous. So from X to U, what can you do? Your idea is this one. Since you have percentile function that is the inverse of the CDF, you have something like this, right? As far as X is a continuous random variable. So you discard that one and say that, okay, first I can convert X to U, and then I can convert U to Y by using the inverse CDF or the percentile function of Y. That is the idea. And I mentioned how can you use this idea to have a nonlinear Z-score generation. Okay? And as you've seen in one of the homework, the two methods, linear Z-score generator and nonlinear Z-score generator, becomes the same if the original input distribution was Gaussian. Anyway, and this is very interesting thing. Actually, in our faculty meeting, we are devising a new faculty evaluation method, and I insist that we use this nonlinear Z-score method, and it's gaining more popularity. So I hope this can be implemented. Anyway, in addition to conventional method to relying on this percentile function or the CDF, we can also have some other method like rejection method and mixing method. And you've seen how the rejection method works in the homework, and now you have better idea. Mixing method is quite obvious, especially if you are a communications engineer. It's like you transmit by using a finite alphabet. So you transmit some modulation symbol, and then you receive the signal becomes a mixture of the Gaussian densities. In that case, you can easily know how can generate that mixture distribution. And this mixing method is to generate some distribution by using, for example, Gaussian, standard Gaussian. You shift that density and you generate some multinomial random variable, and then combine them to have some good mixture distribution. In order to generate a random vector, there are also many methods. The first one is that assuming that you have some random vector generator, very simple. What you do is that you find a good, in general, nonlinear transformation so that the output random vector follows your desired distribution. The problem is that, in general, it is very difficult to find that function. So the trick is simply using the chain rule so that you rely on the one-dimensional random variable generation method. So you use chain rule. So every time you generate a scalar random vector. Of course, you don't need this method if you have the Gaussian output. You just start from IID Gaussian, and then from the very simple lemma that any affine transformation of a Gaussian random vector is a Gaussian random vector, you just try to find good an affine transformation that gives you the desired distribution. The last one is called the Markov chain Monte Carlo method. And that is a very popular method in machine learning and AI. And let me just give you an idea. The idea is like this. You construct a Markov chain, and then you generate a sequence of outputs. And what you do is that somehow you discard the initially generated things, and you take the kind of the most recent ones, and they follow the distribution what you want, something like that. And as we will see in our preview, the Markov chain Monte Carlo method has very famous algorithms called Metropolis Hastings algorithm. And you can find materials like Wikipedia or YouTube videos describing these things. But let me just tell you, what you need to remember is that the Metropolis Hastings algorithm is one of the algorithms to perform Monte Carlo, Markov chain Monte Carlo sampling. And a subset, a class of Metropolis Hastings algorithm is so-called Gibbs sampling, and you can also find some results. By the way, this Gibbs sampling appears in many machine learning textbooks, so you may have interest. But why do we talk about this random number generation under the title of sampling and some limit theorems? Because sampling means a lot different thing. Of course, they are related, but different thing in electrical and computer science and engineering. For example, what is the sampling in electrical engineering? We usually take samples from first continuous time signal to get a discrete time signal. Or sometimes we get some samples from a discrete time signal to a lower rate discrete time signal. Sometimes we take samples to find the so-called sufficient statistic from our continuous time observation or vector observation, something like that. So it's a kind of sampling means dimension reduction in some way. Then maybe a direct evaluation of your input at some point, or some transformed version of your input. Anyway, so this formula is one of the famous things. We know the x sub c is a continuous parameter or time signal evaluated at every T sub capital S, that is the sampling interval. And then you have a discrete time signal. We are kind of familiar with this type of sampling. But here, sampling does not mean this. Okay? This sampling is more about the statistician or probabilistic, mathematical probabilists. Okay? So in Korean, it's for 통계학자 or 확률론을 전공하는 수학자. Got it? So in that case, sampling means what? Sampling means you take measurement. You take measurement to make a statistical inference. So it's more related to what the courses you've taken about the statistical inference. For example, suppose you have a random source. So you have some observation X. However, this distribution is not single. You have a family of distributions parameterized by theta. So so it's like this. Let me use not this one. Yeah. So there is some index set. It could be discrete or countable or uncountable set. But what you want to do is that from observation, you want to know which distribution governs this distribution. For example, in the simplest case, you have a fair coin or biased coin. In that case, you have two different probability distributions. And from the outputs, you observe, for example, IID outputs. Suppose you observe million independent samples and they are all heads. What can you say? Definitely, this outcomes is governed by that biased coin, right? Maybe that biased coin only have heads only, right? Something like that. So in statistics, what you want to do is that we want to find some unknown thing. We want to guess, we want to infer something from the observation. And in order to observe, we take, they say, the samples, okay? So taking samples means sampling, and that means making observations. Nothing more than that, okay? So in statistics and in this section, sample means observation. However, in computer science and engineering, sampling means something different. Sampling means what I just told you during reviewing the last one. Sampling means random something generation. Got it? So they have different terms. Okay. So understand why the important sampling has some strange thing. They generate samples on the important part, okay? Not just uniform. Some part is exaggerated because you divide and multiply by some density. Got it? Anyway, so in computer science and engineering, sampling means generating a random something such as a random variable, random vector, random process. Sometimes what? Sometimes a paragraph, right? Large language model is kind of performs sampling, okay? For example, you have a lot of train, and according to the trained data, there exists some random model. We cannot simply parameterize with some simple finite number or very small number of parameters, but we just want to use that model to generate a parameter, or we have some interactive language model, and that's actually sampling. Got it? So sampling means slightly different things. Here, sampling means making observation. Now, then in statistics, why do we sample? As I told you, we want to guess. We want to infer something from the observation. But there are two types of unknown parameters. This is very important. Of course, the details about this statistical inference will be covered in other courses like 645, which I taught the statistical signal processing course. Or these days, we have mandatory graduate level courses on statistical inference related to AI education. So you can take courses, but what is one of the most important things is that you need to know or first classify what you want to know is random or not. Is it modeled as a random quantity or just a known deterministic number? That is very, very important. So usually the unknown parameter is, even though it is not necessarily a vector, but denoted by theta in statistical signal processing. And if I just use theta, it's of course unknown, but non-random parameter. And if I use capitalized theta, it's of course unknown, but random parameter. Here, what's the definition of a random parameter? Which means that it has a probability distribution. Okay, so you have a probability distribution means that you have some prior information, not only this parameter's range, but also its frequency. Okay. So in this case, you have prior knowledge that can be exploited. Okay. For example, if I ask you a question like how many coins in my pocket, you may say the 0 these days because nobody takes coins, but suppose 20 years ago, so I ask you, your seniors or even your father, so how many coins in my pocket? And you have no idea. In that case, the number of coins is what? Unknown, non-random parameter. But for example, I give you my history, like, okay, for the last 100 days in my pocket, the number of coins has this histogram, like 0, how many days, 1, how many days, something like that. And I give you that information. And then you have prior knowledge about that one, and you can model it a random variable. In that case, you have what? Random parameter to be estimated. Got it? So that's the difference. And second one is that what is the set of this random parameter? For example, this theta may be, we have, in addition to whether we have a random or non-random parameter, in that case, in non-random case, we have to say something like this because the theta is not random. But in random parameter case, we have some realization. But anyway, this theta are, for example, random vectors, and they may be a set, they may be a member of an index set. And this set, as I always emphasize, can be a finite set or countable set, countably infinite set, or uncountable set. According to this countableness or uncountableness, we divide our inference problem into two. If we want to estimate a parameter from a countable set, the problem is called a detection or classification problem. By the way, in statistical signal processing, detection problem is quite more often used. In machine learning AI, they say classification problem. If the index set is uncountable set, in statistical signal processing, this is called an estimation problem. In machine learning, sometimes it's called regression problem, even though regression is not the only estimation problem. Okay, so you can divide the problem into 4: random or non-random parameter to be estimated. And the parameter is from what? A countable set or an uncountable set. Got it? For example, in data communication, usually we assume that our information bits are random, 0 or 1 with equal probability. In that case, after we observe the, for example, output of our antenna, we want to find out what was the bits, 0s or 1s. In that case, we have definitely a random vector. So it's a random parameter inference problem. And now each bit can be 0 or 1. So our index set would be 2 to the length of this bit sequence. It's finite. So we have a detection problem. Of course, sometimes this estimation, the term estimation has a wide sense meaning. So even detection is called estimation. But I prefer using inference. So statistical inference can be divided into detection and estimation. By the way, the capability of inference capability means intelligence, actually. What else can you define in terms for the term intelligence? I thought about it when I was an undergraduate student, but anyway, these days, intelligence, even artificial intelligence, means the capability of making statistical inference. And there are mostly 2 things only: detection, estimation, or classification and regression. So statistical inference is very closely related to the artificial intelligence. Those machines, models are actually estimators and detectors. Got it? By the way, the term an estimate is used not only for estimation problem, but also for detection problem. So let me give you a block diagram. So here is your source governed by some unknown parameter. Source governed by unknown parameter. It could be random or non-random. Now you make an observation. And what you do is that here you have a system. You want to build a system that takes this observation. It could be IID sequence of random variables or a finite random vector, anything. And this one makes the inference and gives you an estimate of the parameter. Got it? So this is called sometimes detector and sometimes called estimator, depending on whether this data is a member of a countable set or uncountable set. So this is called an estimate. Okay. Of course, this estimate is what? A function of its input. So sometimes they put parenthesis x. Okay. And usually this block is a deterministic mapping rule. However, it is not necessary. So it can be a random mapping rule. In either case, this output, an estimate, is a random thing. It's a random vector if theta is a vector. If theta is a scalar, it's a random variable. So you have the idea. In AI and artificial intelligence, much focus is much focus is on how to build this detector or estimator by using so-called training. But in statistical signal processing, in most of the cases, we derive mathematically what would be the best estimator or detector based on our mathematical model of this X, parameterized by unknown theta. That's the difference. However, more and more researches are kind of have showing convergence of these two. Not only the mathematical model, but sometimes we have a lot of things about this without knowing the distribution at all. In that case, we need two things if we just consider classical statistical inference. We need to mathematically model the source by using a lot of data. And then from this one, we have to find an estimator, good estimator. The machine learning and AI, deep learning, they have different approaches. What they say is like this. Suppose we have some restrictive but very versatile, it's complicated but conflicting, but structure they call model. And this model can be trained, which means that this model has a lot of parameters, and that parameters can be optimized by using a lot of observations. And then they put it here and use it as an estimator or a detector. That is their idea. And the current trend is to use the neural net or neural net-based models to build such a train-based detector or estimator. Anyway, here in this course, I will say this output of the detector or estimator as an estimate of the parameter. Got it? About the detection, you can take the other courses like statistical communication course or the statistical signal processing. So in this section, we focus on estimation of especially non-random parameter. So as I told you, there are two things, four things. First, detection, random, non-random parameter. So parameter, non-random, and random. Here, the index set, countable, uncountable. So here, we are interested in here. Got it? We want to estimate a non-random parameter. And that non-random parameter is a member of an uncountable set. For example, a real number, something like that. And also, since this section is very short, we are not covering every possible estimation problem, but we focus on only two things actually. But anyway, the textbook shows, of course, our undergrad textbook shows important terminologies you need to know. So here, let's review these terms again. This X is called, of course, random observation. Okay, so random observation. And you have a set of unknown parameters. That set is this index set. And you have an estimate. This is the output of your estimator or detector. And since you have this uncountable set case, this is called estimator. But it could be called detector if our index set is countable. Got it? Now, I'd better give you a concrete example because otherwise we will have a lot of confusion. So let's directly move to our example. Suppose we have random sequence generator. And this random sequence is, for example, not necessarily Gaussian, but has mean mu. So they are IID, for example, IID random variables having the same mean and variance. Okay, the distribution is not that not important in here. And now you have IID samples. And what you want to infer from the observation is that these two parameters. Got it? So from a lot of IID samples of a random number generator, you want to estimate mu and sigma. By the way, let's just assume that this generator is a Gaussian random number generator. Then how many different random number generators do you need? In theory, uncountably infinite, because there are uncountably infinite combination of mu and sigma square, right? Of course, you know that you need only one IID, standard Gaussian random number generator. In that case, you multiply the standard deviation and add the mean, and you have the parameter. So you may say that this box is actually decomposed this way. Right? In that case, you can easily understand, okay, so I really want to find, yes, these two values in this system. Got it? And these two numbers can be any number. Mu can be any real number. Sigma can be any non-negative number, right? So you have how many combinations? Uncountably infinite combinations. Got it? So this is an example of an estimation problem. So what do you suggest to have a good estimator here that generates what? So suppose you have a lot of things, length n, for example, and then you want to generate what? You want to generate estimate of mu and estimate of sigma or sigma square. So let's say sigma square hat you want to generate, okay? In this example. So what you want to do is that you take, for example, n IID observations. So let's say that this x is simply x1 through xn. So you take n IID samples, and then you want to build a box that takes these inputs or that samples this distribution, okay, in computer science and engineering terminology. And then you want to generate two estimates, or sometimes you can just put this parameter mu and sigma square together as a random vector. In that case, you want to generate a vector estimate of a vector parameter. Got it? Now, the simplest estimator would be what? As you know, you can rely on the law of large numbers. So what about just take the arithmetic average of these samples, x1 through xn? So you may say that, okay, the upper branch could be something like this. So mu hat of x1, x2, xn may be defined as something like this. Here, actually, this means you have observation. So this one is the input actually, right? However, you don't know what will happen. So your input is still has uncertainty. So you have random input. So even though your estimator, this is an estimator, is a deterministic function of the deterministic realization, the realized deterministic numbers, actually you have what? You have a random number generator. That depends on the input random vector. Anyway, and let me ask you a question. So is this have a good property? Yes. In what sense? It converges to the true mean as n tends to infinity, according to the law of large numbers. If we rely on strong law of large numbers, we can say that that convergence is almost sure sense. If we rely on weak law of large numbers, then we say that the convergence in the in probability measure or in probability. The problem is that this kind of asymptotic convergence to the true value is not guaranteed. And we can easily see from this example. Suppose you design this estimator. What do you guess? So what you do is that in the upper branch, you compute the arithmetic mean. And in the lower branch, you take this value and subtract, and then you square and sum each value, right? You take the upper branch output and subtract from each sample and square and sum up and divide by n. What do you guess? Actually, you still have, due to the law of large numbers, and one more thing, you have the convergence actually. However, the problem is that sometimes we cannot take as large samples as we wish. We have to truncate. So not only this asymptotic convergence, sometimes people love to have this one, this property. So if we just take the expectation, sometimes we want this one. Be careful. Upper two things are different from lower two things. Okay? This means with even finite number n, you have on average, that is mu. Be careful. Mu can be anything. So in your search space of mu and sigma square, right? This infinite search space, your parameter can be any point, right? For any point, this estimator has this property with finite n. The problem is that this is not true. You can easily say that this is, let me see. Something like this. Yeah. So you have, of course, if n is large enough, this is very close to 1, so you can ignore this term. But precisely speaking, this estimator does not have nice property. So if you choose some point, and if you have some finite number of samples, then its expected value is not same as sigma squared. Of course, it converges. So that kind of idea is defined for the estimation of non-random parameter. So let's see these terms. The first one is this one. An estimator is unbiased. What does that mean? If the mean of the estimator equals the quantity being estimated. This is what I just told you. So let me formally state. So you have estimator, and be careful here. This part is often ignored even by the instructors and the students for all data in the index set. Okay? This is the most important thing. Say that if you change theta, distribution changes, right? But you don't know which distribution is selected among uncountably infinite candidates. And this unbiasedness of your estimator. So you design a fixed theta hat, and you test whether this is true for all theta in the set of parameters, the index set of parameters. If this is true, then that estimator, theta hat, if this is true, then what? Theta hat of x as an estimator. This is a function, deterministic function, an estimator is called unbiased. By the way, the reason why this is called unbiased is that if you subtract, then it is 0. 0 means no bias. And another thing is that this part can be rewritten in this way. Because theta is not a random parameter, it can go inside the expectation. And in many cases, this quantity enclosed by the parenthesis is called error. Of course, some people love to change the order of these two, but I love this one, true value. How much deviation from the true value? That is, I prefer to call an error. So error is 0, what? For all theta. This is a very, very strong requirement, okay? So if you just choose arbitrary estimator, it can never be an unbiased estimator. Got it? So unbiasedness is a desirable property, but it's hard to meet in general. Of course, if you are given a very easy problem, it's very easy to find unbiased estimators. So now you understand what's the meaning of unbiasedness. So for every parameter point that is unknown, your estimator gives you the expected value that is correct. Okay? And second one is a little bit relaxed version in one sense, but it's a much stronger version in other sense. Let's see. The sequence of estimators is consistent. What does that mean? You have single estimator. Why we said sequence of estimators? Because in many cases, this estimator takes a finite length vector, but that can be easily generalized to for different lengths. For example, suppose you use an arithmetic mean, then that estimator can be easily generalized. You just change the denominator and numerator, right? So you may put something like this. In that case, this nth estimator is unbiased, right? And or you may have the entire sequence of estimators parameterized by n may be unbiased. Got it? So be careful. But here, sequence of estimators, theta sub n of x is consistent. What does that mean? This is stronger in the sense that you are not talking about, it is not necessary. You may talk about it just using something like this, converges to theta for all theta in the index. So in this case, what? This is a random quantity, right? And this is non-random thing. So it's like something like strong law of large numbers or weak law of large numbers. So it's a convergence of a sequence of random vectors to a vector. But this could be too strong. For example, this convergence is about almost sure sense or equivalently with probability 1, then we say that the sequence of estimator is consistent. In what sense? Almost sure sense. In other words, strongly consistent, like strong law of large numbers. So strong consistency talks about almost sure convergence. Second one is mean square convergence. So you have is what? You take the mean of square of course, error converges to 0. Again, for all theta in the index set. So whenever you talk about a non-random parameter to be estimated, be careful about your condition needs to be met for all theta. So the second one is consistency in the sense of mean square in the second mean. And as you easily guess, hey, I can devise kind of consistency in probability. Of course, you can do that. That is called weak consistency, as we say, weak law of large numbers. Another thing is that asymptotic unbiasedness. By the way, in the weak consistency, we have for every epsilon positive probability of the event greater than epsilon converges 0, something like that. The fourth one is interesting thing. This is unbiasedness combined with consistency. So in order to talk about unbiasedness, you need to take the expectation, right? And then this converges to theta for all theta in the parameter set. This is called the asymptotic unbiasedness. This is one of the easiest consistency. Got it? So depending on your requirement, probably you choose one of the consistency properties, or you just ignore them. However, usually people have interest in whether this estimator is robust or not. This consistency, unbiasedness is all about robustness. The parameter can be chosen from the index set at any point, right? And that estimator must work well for any choice of the parameter, because you don't know which one will appear, which one will be chosen in the generator, right? So these are desirable properties, unbiasedness and consistency. Now let's go back to our example, because we are not taking the estimation and detection theory course, but the probability and random processes course. By the way, I just talked about the unbiasedness only, but that is not enough. So what we do is that among unbiased estimators, we want to choose one of the best unbiased estimator. That is one of the idea of minimum variance unbiased estimator. So among unbiased estimators, we want to find out the estimator that gives the minimized error covariance matrix for each theta, for each choice of theta. However, whenever we define something with A and B, there is a likelihood, a possibility that nothing exists that satisfies that condition. So given a problem, you may not have minimum variance unbiased estimate. That is the problem. Fortunately, our previous case of, now let's generalize, uncorrelated observations with same mean and same variance. Both are finite. We want to find an unbiased estimator that has minimum variance. Fortunately, you can find that arithmetic mean estimator is an unbiased estimator for the mean part, and the so-called sample variance estimator is the part of the minimum variance unbiased estimator on the lower side. So be careful. What you want to do is that we set theta equals mu and sigma square, okay? And we want to find some theta head of xn. Here, n means you take n of them. Of course, this may be a function, two functions, right? Some function of xn and another function of xn. Here, we use the sample mean, sample variance estimator. Sample mean estimator is very simple, but sample variance estimator is quite strange. See that? You have n minus 1 in the denominator. What does that mean? This does not work if you have single sample. And it is obvious, right? Suppose you take just one sample from a random number generator. How can you guess its variance, right? That is reflected in this idea. And the notation is quite sloppy, but you can show that this estimator that use the estimator for the mean. Be careful, this is not the true value. This is also an estimator of the mean. You can show that this is an unbiased estimator. And also, since as n tends to infinity, this sigma is 0 by using the Chebyshev inequality, you can show that this is an consistent, not only the unbiased estimator, but it's a consistent estimator, something like that. By the way, when I was taking the statistics course, when I was an undergraduate course, sophomore undergraduate course, one of the final exam problem was to prove that this is unbiased. So I had to take the expectation and manipulate all these things and show that this equals sigma x squared. And I missed it. And I gave a wrong answer anyway. And then immediately after the exam ended, one of my classmates asked me, "Hey, Juno, how did you solve it?" And I explained that. And he said, no, that's not correct. And according to him, I got angry and just shut my mouth and left the classroom. That's what he said in 30 years when we met. Anyway, I remember I got angry at that time, but I didn't remember that the person who asked was him. But anyway, so this is a good exercise problem, and you can find from any standard statistics course. So let's go back to preview part. So I've just covered this part, except the method of moment estimator. And let me talk about this one. Suppose what you want to estimate from the samples is a function of the moments. Then the simplest one is something like this. Suppose your theta to be estimated is related with something like this. Okay? Then this method of moment estimator suggests you to take the arithmetic mean squared something like this. Can you see the idea? Each moment is replaced by its law of large numbers estimator. See that? expectation of x according to the law of large numbers is what? Arithmetic average of xi's. So here it goes, right? Let me use capitalized x. What about expectation of x squared? It's the arithmetic average of x squared, x sub I squared. So you have it. Got it? So this is this simple estimator. This method of constructing an estimator is called method of moment. So you use moment, relying on the law of large numbers. The problem is that most of, according to my experience, most of the method of moment estimators are biased estimators. So you need to be very, very, very careful. Got it? For example, the sample variance, the primitive version, was what? Was doing something like this, right? So sigma x squared, be careful, sigma x squared is defined as what? X minus x bar squared, right? So according to the method of moment estimator, you first, hey, what is this? This is 1 over n sigma xi squared, xi. So you may want to say that, okay, this may be 1 over n sigma I from 1 to n xi minus that one, 1 over n sigma j from 1 to n xj squared. This is biased. As I told you, in order to remove bias, you need -1 here. Got it? So be careful when you use a method of moment estimator. According to my experience, mostly they are biased. So sometimes I handcrafted, scaled that part because of this experience. Just a little bit of change, like 1 over n removes 1 over n minus 1 removes the bias. So I just sometimes try after I build a method of moment estimator. Anyway, so that's it for the chapter 7. And now we are going to move chapter 6, which fortunately will not appear in your quiz. Here we go back to our old friend, the undergraduate textbook, but the materials on this handout are much extended versions of it. We are going to shuffle our covering order of the sections. So we first cover sections 1 and 2, and then move to 5 and 6, 7, and go back to 3, and some part of 2, and then 4. So first, what is a random process? Let me ask you, what is an undergraduate version of your random process definition? So what was the definition of a random process? In our undergraduate version, random something. So whenever you have random something, you always said something with uncertainty that is modeled probabilistically. So for example, suppose this is a random variable, then you say that, what is a random variable? As an undergraduate student, you say that a variable or a scalar with uncertainty that is probabilistically modeled, right? What is a random vector? Vector with uncertainty modeled probabilistically. What is a random matrix then? Matrix with uncertainty that is modeled probabilistically. What is a random graph? A graph with uncertainty. Again and again and again and again, same thing. Actually, that is good because that is not incorrect. That is just imprecise, okay? So as we do, what is a random process? Here goes the problem. What is a process? So we'd better say random signal or random waveform, okay? So, or a function if you want. So if I say If I ask you, what is a random signal? You may say that a signal with uncertainty, whose uncertainty is modeled probabilistically, right? So now you have a signal that has uncertainty. You have a waveform that has uncertainty. You have a function that has uncertainty. However, your graduate version always relies on what? Box, sample space, event space, probability measure, and your outcome S, and then what? You have a mapping rule. This mapping rule is what? From the sample space into some set. And this set, depending on what is this set, your outcome's name, output's name was determined. For example, this was a set of real numbers. Then what did you call this mapping rule? Random, real random variable, right? If this is a set of complex numbers, you would have said that this is what? This function is a complex random variable. If this set is a collection of vectors, you may say that this is a random vector. Now, let me ask you a question. What about the case where this set is a collection of continuous time signals? You may call this one, this mapping rule, as a random continuous time signals or random process. Got it? So, depending on this one, your name differs, but now this set is called this has a special name when we deal with a random process. This is called an ensemble. Of course, of sample functions or sample paths, sample waveforms, depending on sample signals if you want, anything. Got it? But sample path is one of the most commonly used term, an ensemble of sample paths. Now, if you plot the output, what it would look like if that ensemble consists of continuous time signals, then your output would be some continuous time signal. And this signal is a time function, so you want to say that, okay, this is x of t, but it depends which continuous time function is to be selected is determined by this outcome S. So you want to write in this way, right? For each function, for each sample path. But whenever we talk about not just the single output, but that signal with uncertainty, we modify that X into a capitalized one. So this would be a good notation for our random process. So in some textbook, people love to use capital X subscript T, that is time parameter, and parenthesis S, they always have done for major theoretic random something definition. As you remember, capital X of S for random variable, capital X underline of S for random vector. Same, capital X of T to denote that it's a time function. Now, you have parenthesis S. The difference is that sometimes you want to handle continuous time signal, sometimes you want to handle discrete time signal. So in that case, they say that, hey, okay, let me use some time parameter. This is a kind of bold-faced T I really hate. And this T could be what? The set of real numbers. In that case, we have a continuous time signal. It could be the set of integers. In that case, we have a discrete time signal, something like that. So instead of using T, let me just use like sometimes R, sometimes Z, okay? So you can easily notice that we not only can handle continuous time and discrete time signals with parameter t, which means time, we can also generalize it to like continuous parameter.
Dr. Joe, it is time to wrap up.
So random continuous parameter signal, random discrete parameter signal, something like. See that? This is, in this case, you can say that this is a time parameter. So continuous parameter random process, discrete parameter random process, you can name. Anyway, about more of the definition, we are going to cover it on this Thursday. But anyway, it's a kind of important day for me because now we have started to cover the random process part. Okay, that's all for today.